It's a pleasure to have Guillaume Tahar. He's an assistant professor in geometry topology group who is going to talk about isoresidual fibrations.
Thank you very much for your invitation. Today, I'm going to introduce you to an object, a natural construction in the study of moduli spaces of differential forms on Riemann surfaces. We constructed it in collaboration with Quentin Gendron, who is in Mexico now. The simplest way to introduce you to this object is to start with something probably everybody knows. When you have a polynomial, P, you can describe it in terms of its coefficients or in terms of roots. If you know the roots of a polynomial, it's easy to deduce the coefficients. But if you know the coefficients, to give an exact formula for the roots is, in general, quite difficult because the symmetry group of the equation of the polynomial equations, the Galois group, can be quite complicated. Okay, so these two formulations are in principle equivalent, but in practice they are not. I want to discuss a third point of view on a polynomial. A third way to describe a polynomial is to take the associated differential form dz over pz and to look at periods of this differential around well-chosen loops, in general, residues at the poles of the differential. This point of view has been recently used to study groups by Nick Slater in a recent talk he gave in Tsinghua University. So probably some of you have already some intuition of that. And so we have 3 points of view on a polynomial. And the asymmetry between the arrows connecting them can be measured by the complexity of the monodromy group of a ramified cover. Okay? So this is the topological formulation of Galois theory. Yes? I mean that when you know the roots of a polynomial, you can deduce the coefficient, but when you know the coefficient, you know the roots up to some symmetry, and you need to break this symmetry to get explicit formula. Okay? In the example formed by the isoresidual fibration, you have the moduli space of differential. Yeah? Provided the dimension, provided the number of degrees of freedom are the same, yes. Yeah, this is a chapter of Galois theory. Yeah, absolutely. So the example I'm going to discuss is in the moduli space of differential forms. We describe a differential in terms of the location of its roots, and we will define the residues at each pole. This map will be a ramified cover with a non-trivial degree and with a non-trivial monodromy group. Okay, so let's give a few definitions. Omega M will be the moduli space of meromorphic 1 forms on CP1 with P labeled poles. Poles are labeled to avoid problems of symmetry. of orders B1 to Bp, and a unique zero of order what you need to satisfy the global degree condition of a meromorphic differential. Okay, so we are in a very specific situation where your differential has only one big zero and several poles. Okay, it is because we are thinking about differential forms of the form dz over pz, where p is a polynomial. Okay? Following the description in terms of location of the roots, this stratum is a product of C star with the configuration space of p minus 2 points in the sphere. Okay? Because you can just put your unique zero at infinity, the two first poles in 0 and 1, because of the projective automorphism of CP1. And then you know your differential up to a global factor corresponding to the product with C star in the description of this moduli space. Okay? A configuration space of finitely many points on the sphere is a complex manifold. Complex or bifold if you allow symmetries, okay? That's why we label the poles. And its topology is quite, okay. Its topology is quite easy to describe, okay? The isoresidual fibration here is defined as the map that associates to every differential the list of its residues at the p-poles. No. They don't need to be simple. You have a pole of arbitrary order as a well-defined residue. It's just correspond to the integral of the differential around the simple pole. Okay. These residues sum to 0. This is the residue theorem. So omega and Rp have same dimension p minus 1. There is a typo here. So the isoresidual fibration is a ramified cover. Okay? So I hope that now I have convinced you that if we want to study the relation between the periods point of view and the roots point of view, we need to look at this map and understand it geometrically. So what is the ramification locus of this map? What is the degree of the cover? And what is the monodromic group of this cover? You can also rephrase the computation of the degree in the following terms. I have a configuration of residues, or a configuration of p residues summing to 0. How many differential with only 1 0 realize this configuration of residue? The answer is a finite number. We need to compute it. Okay? And surprisingly, the answer is geometric. The idea to answer all of these questions is to translate a problem about meromorphic differentials, a complex analytic object, in terms of a geometric structure called a translation structure. Okay? Translation surfaces are now a quite classical topic in mathematics. They have been well studied by Kontsevich, Zorich, Eskin, Mirzahani, mostly in connection with dynamical systems. Okay, a translation surface, the archetypal translation surface is a flat torus formed by identifying the opposite sides of a parallelogram. These kind of objects are quite interesting because you can define a dynamical system on it that modelize billiards, for example. And what is interesting with them is that they correspond to complex analytic objects. Indeed, when you decorate a Riemann surface with a meromorphic one form, on each open set that is disjoint from the zeros and poles of the differential defines local primitives. And these local primitives are well defined up to addition of a constant. Algebraically, addition of a constant complex number is exactly the same thing geometrically as a translation in the complex domain. In other words, local primitive functions of a given meromorphic differential on a Riemann surface defines an atlas of local coordinates where transition maps are translation. Okay? This translation atlas is defined on the complement of zeros and poles of omega, and there is a complete classification of the geometric, there is a complete description of the geometric models of these singularities. Okay? So we are going to describe the meromorphic one forms of our isoresidual fibers in terms of this geometric structure. What's important here is that every geometric notion of the complex plane that is invariant by translation, every geometric notion, angles, length, parallelism, slopes, straight lines, makes sense on a translation surface. Okay? So the addition of a meromorphic one form rigidifies the Riemann surface. So a translation surface is essentially made of flat polygons glued on each other by translation. And in particular, they are endowed with a flat metric, and this flat metric has well-defined geodesics. And we will see that the geometric and combinatorial description of this geodesics will allow us to distinguish elements of the same fiber. The nicest singularities are the conical singularities, okay, conical points like on a polyhedron, and they correspond to the zeros of the differential. And a saddle connection will be just a geodesic, a simple geodesic joining two conical singularities. You can think about them as the edges of a polyhedron or the diagonals of a polygon.
Can I ask you a question? So your base in here is one complex dimensional?
Yeah.
Always?
What do you mean? These objects
meromorphic differential form is always over a complex curve.
Yeah, on a Riemann surface. Absolutely.
So then outside of the poles, this thing is essentially just a twist of the trivial bundle.
Yeah.
And then if I look at charts and I go from one patch to another, I am at most multiplying by non-zero complex numbers. I can define that always as a translation. So this is somehow given.
Hmm?
Yeah, you make a but then what is special about translation structure? So you just make a choice of a form or a fixed choice of a translation. That's it?
No. What I'm saying is that a meromorphic one forms endows a Riemann surface with a translation structure. It is an atlas, a geometric structure given
always,
by an atlas.
Absolutely, always. That's true.
Yeah.
Okay. But this is given, right?
No.
Well, meromorphic one form outside of the poles is basically a copy of the trivial bundle.
Yes.
Maybe with some zeros here and there. So if you look at these fibers over patches, you go from one to the other, it's always basically a multiplication by non-zero complex. So I think I'm not understanding what is not trivial. But I think definitely there is something I'm not getting. So you have the complex curve, right?
Yeah.
Okay. You have the meromorphic one form, and then outside of the poles, this thing, let's say it doesn't have any zero. This has poles.
Yeah.
Outside of the poles, I think it actually needs to have zeros. It has zeros, And outside the poles is just a twist of trivial bundle by some degree, minus degree, negative degree. And that's a line bundle on that curve. And then going from one patch to the other, transition maps are just multiplication by non-zero complex.
Actually, it's not multiplication by a complex number. It is addition.
So you want it to be addition. Can I always? So it's the structure.
Yeah.
So what is being added in here? The fibers, right?
No.
You shift add over the surface. Okay, got it.
Take the example of the flat torus. Okay. So in the flat torus, the period of your differential along a couple of loops forming a basis of the homology. The periods of the differential along them is just the translation that identify the two opposite sides of your parallelogram.
Okay,
exactly.
I understand. It's the period which is
getting exactly. Okay. That's
not
why the translation structure is exactly the kind of geometric structure you need to study the periods of a differential and the periods point of view on a polynomial. Okay. So we'll be especially interested in saddle connections because they will form the skeleton of your translation surface. Okay, a saddle connection is just an edge of your polyhedron, for example. And what's important with them is that they correspond topologically to an arc on your surface joining two special points. And so your differential has a well-defined integral along this arc. And in the flat metric, the length of this saddle connection corresponds to the modulus of this integral, and the slope that is globally defined in the translation surface of your saddle connection is the argument of this period. Okay? So actually, a meromorphic differential defines a geometric structure, and the geometric structure gives you a set of geodesic lines that directly encompass the information about periods. Okay? In particular, because this saddle connection generates the homology of the surface. So there is a dictionary between complex analysis and flat geometry. A pair X omega corresponds to a translation surface. A zero of order m corresponds to a conical singularity of angle 2m+1 pi. A simple pole is a point at infinity in an infinite cylinder, and a double pole corresponds to the end of the infinite flat plane. Okay, in the point of view of translation surfaces, the infinite flat plane is CP1 endowed with dz that has a double pole at infinity. Okay, and so the slope and length of the saddle connection are the argument and modulus of the period of the corresponding relative homology class. O1 forms have only one zero, so saddle connections are based loops. Okay, a saddle connection joins two conical singularities. Here we have only one, so each saddle connection is just a based loop. It encompasses a based loop in a sphere in CP1 cuts out your sphere into two parts, each encompassing some residues. So periods of saddle connection are just partial sums of residues. And we understand here that we'll have problems, or surface will risk to be singular if some saddle connection shrinks to have zero length. And this corresponds to the vanishing of a partial sum of residues. In other words, the space of possible configuration of residues, the base of our isoresidual fibration, is a very simple complex vector space that contains the so-called resonant arrangement a complex hyperplane arrangement defined by the vanishing of every possible partial sum of residues. Okay? And it will be the ramification locus of our isoresidual fibration. So the idea is that our stratum or moduli space is quite simple to describe. It depends only on the number of poles. Downstairs on the base, it is a complex vector space with this arrangement that is also quite easy to understand. No, not quite easy to understand. It is we know almost nothing about it, but it depends only on the number of poles. It does not depend, for example, on the degrees of the poles. Actually, this resonance arrangement is a kind of mirror of the braid arrangement. There are relations between them, a kind of duality. Okay, so this is the ramification locus of our fibration. But to understand the degree, to compute the degree of this map and understand the monodromy group of this fibration, we need to perform another reduction. We already reduced a complex analytic problem to a geometric problem. But now we are going to reduce the geometric problem of describing different differential realizing the same configuration of residue, okay, to compute the degree. We are going to reduce this problem to a purely combinatorial problem. The resonance arrangement is defined by real equations, okay? Partial sums have coefficients that are 0 or 1. So they are real equations. This implies that generic configurations of real residue lie outside this hyperplane. So when we want to compute the degree of a ramified cover, we choose our favorite fiber. The idea is that real residues are nice and generic real residues are generic enough to allow us to compute the degree of the fiber above them. Okay? When residues are real, the period of the saddle connections are real. And so every saddle connection is horizontal. And since every saddle connection is horizontal, they cannot cross each other and decompose especially nicely the surface. And it's quite easy to prove that the translation surface corresponding to a differential with only real residues is just the gluing of p topological disks, one around each pole, along p minus 1 closed saddle connections. So elements of the same generic isoresidual fiber will be distinguished by a combinatorial invariant that is essentially the embedded graph in our surface corresponding to the saddle connection. And this is really given by the flat metric. It is given by the geometric structure and used by the differential. Okay? Each element of an isoresidual fiber of a real configuration of residue is described by a decorated tree. We just take the dual graph of the embedded graph formed by the saddle connection, and we add some decoration to take into account angles that are integer multiple of pi bigger than pi. Okay, so we need to add some half edges, but essentially it amounts to count trees. And we can compute the degree of the isoresidual cover this way. Okay? Okay. The monodromy of the cover for loop around a resonance equation correspond to a combinatorial operation of the set of decorated trees. Okay? In our trees, each edge corresponds to a saddle connection. Each saddle connection corresponds to the vanishing of a partial sum. And the resonance hyperplane corresponds to the vanishing of a specific partial sum. So when you turn around a resonance hyperplane, this amounts to cut the edges of your tree corresponding to this very partial sum and move them around the rest of your tree. So this combinatorial operation corresponding to I can draw a picture. This is a decorated tree corresponding to some differential. You have 5 poles, 5 domains of poles. Each one is a disk. The edges corresponding to saddle connections. And these saddle connections have a period that is a partial sum of residue. So when you approach a resonance hyperplane, some of these edges will shrink. And the corresponding surface will degenerate to a nodal curve, okay, because some edge is shrinking. What's going on then is that this edge will be cut and move elsewhere, depending on how many terms you are performing around your resonance hyperplane. Okay? So the computation of the monodromy of this cover can be completely translated into combinatorial operations on graphs. We have a formula. We deduce a formula to compute the degree of this cover. So for a stratum with a 0 for the A and P poles of orders B1 to BP, the isoresidual fibration is a ramified cover of degree A factorial divided by A plus 2 minus P factorial. And it is ramified over the resonance arrangement. A is the degree of the pole. A is the degree of the unique 0. Okay, so in particular, A is the sum of the BG minus 2, okay, because we are on CP1. In general, the monodromy group of this fibration is big, but we observed that for a very specific stratum, a stratum formed by differential with a sextuple 0, 2 triple poles, and 1 double pole, the isoresidual cover is of degree 6. And actually, the monodromy group is a very specific subgroup of S6, of the symmetry group over a set of 6 elements. It is the exotic embedding of S5 into S6. Okay, you know that when you are working with permutation groups, it's quite easy to embed Sn into Sn plus 1, just as a stabilizer of 1 point. But is it possible to embed Sn into Sn plus 1 in a way, in a transitive way, in such a way that the group acts transitively on the n plus 1 elements? And actually, this can only happen for the embedding of S5 into S6. It's called the exotic embedding. And it appears naturally as the monodromy group of this fibration. Okay, it's not a curiosity for algebraists. It really exists. It really exists here. So this story can be generalized in higher dimension if we consider strata of differential with several zeros. Okay, when the degrees of freedom in your stratum is higher than the dimension of the space of configuration of residues. And in this case, isoresidual fibers are no longer discrete sets. They are complex manifolds. Because you have p-1 degrees of freedom for the residue of the pulse and periods of arc joining distinct zero. That gives you another n-1 degrees of freedom. Isoresidual fibers are complex manifold of dimension n-1. And since the period of arcs joining distinct zeros depend on the choice of the arc, they are defined up to addition of absolute periods. And this is actually what you need to define a translation structure, but in higher dimension. My general goal, in fact, is to exhibit isoresidual fibers in higher dimension as families of examples of higher dimensional analogs of translation structures on surfaces. Okay? So, in the case of strata with 2 zeros, the additional degree of freedom is just the period of an arc joining 2 zeros. And also, our fibers are complex curves endowed with a natural geometric structure. Here, a translation structure. So isoresidual fibers are translation surfaces parametrizing translation surfaces. And we have an interpretation of their singularities in terms of the degenerations of the underlying parametrized objects. So in a translation structure, we have two kinds of singularities, zeros and poles. And since our isoresidual fiber parametrizes translation surfaces, where the degree of freedom is the period of the arc between 2 zeros, you have two possible degeneration. Either the 2 zeros collide or they go infinitely far from each other. In one case, the fiber develops a zero, conical singularity. In the other case, it develops a pulse. And the consequence of this is that since each isoresidual fiber has a translation structure, and translation structure corresponds to a meromorphic one form, we're able to compute the genus of each generic isoresidual fiber for such a fibration because of the interpretation of the geometric structure on the fiber in terms of degenerations of the space it parametrizes. Okay, so it gives a moduli theoretic way to attack the description of the geometry of the fiber of this object. That is quite easily defined. Every differential of a stratum can be parametrized by the location of the roots. So it is algebraic geometry. It is polynomial equations. But in practice, they are very hard to solve. So this is a combinatorial way to deduce topological information on the shape of the fibers. We can even go further and consider isoresidual fibration in case of strata with 3 or more zeros. And in this case, we have just one example. For stratum with 3 simple zeros and 5 simple poles, computation indicates that isoresidual fibers are K3 surfaces, and K3 surfaces coming with an additional geometric structure inherited from the period atlas, from the description as the moduli space of translation surface depending on the relative position of 3 zeros this time instead of 2. So again, here isoresidual fibers are complex manifolds with a geometric structure. And in this case, the singular locus of this geometric structure is no longer isolated points, zeros and poles, but rather a more complicated locus that we hope to describe combinatorially, and we hope to be soon able to compute the main discrete invariants of these fibers in terms of the combinatorial data that define the stratum. So just like we were able to compute the genus of isoresidual fibers when they are curves in terms of the degrees of the zeros and poles of the stratum, we expect that we can compute Chern and Hodge numbers of these fibers, again, in terms of the degrees of zeros and poles defining the stratum. So this case of K3 surfaces endowed with a flat structure, with a translation structure, is, in our mind, the first example of a general program whose goal is to find a reasonable category of translation manifold generalizing translation surfaces, to be able to generalize the theory of translation surfaces, and including the dynamical aspect. And the problem is we need to find objects that have at the same time a complex analytic interpretation, okay, like a Riemann surface endowed with a morphic differential, and a geometric side, a topological manifold endowed with an atlas with constrained transition maps. The first candidate developed by Dima Panov in his PhD dissertation was called Kähler polyhedral surfaces, but were quite rich from a point of view of complex geometry, and for which we had formulas to compute the Chern numbers. The problem is that these objects, this Kähler polyhedral surface, are obtained by gluing polyhedra. Okay, so these are typically objects that are, in their very definition, geometric objects. In contrast, isoresidual fibers come from a moduli space whose nature is complex analytic. So our idea is that any reasonable category of translation manifold that should generalize translation surfaces should include generic isoresidual fibers of strata of morphic differential as examples. Okay, maybe I've been a bit too long. Thank you very much for your attention.
Okay, any questions?
Sorry, this is just a question born from ignorance. So there is a combinatorial structure in this problem also, which can be realized in terms of combinatorics by computing correlators in matrix models. Right? I mean, combinatorics of graphs can be put into a correspondence with correlators of matrix models.
I know a little bit about this story, but it's not directly related to this. In the theory of translation surfaces, there is a computation of the volume of this strata, yeah, in terms of correlator, just like to describe. It is the idea is to consider in the moduli space of translation surfaces square tile surfaces that are ramified covers of the square torus. And since these surfaces fill them, if you take smaller and smaller tori as units, you get asymptotic formula to compute the volume of your moduli space, and each square tile surface can be described combinatorially because it's just a ramified cover of a torus. So, but in some sense, it is far more complicated than the object I'm describing today.
Right, but I was just wondering that because it's easy to, well, relatively easy to dial parameters in the space of matrix models, right? You can add and subtract terms in the action as you wish.
Mm-hmm.
Then maybe that could be a way to explore the space of these theories.
Actually, what you suggest correspond more or less to an enumerative geometric point of view. And there is a story about that. Actually, we are two teams that were competing at the beginning to compute the genus of these isoresidual fibers. With Quentin Gendron, we used interpretation in terms of moduli spaces, and Dawei Chen, a student Miguel Prado in Boston College, used enumerative geometry, integrated cohomology classes, and it took us months to obtain the same results at the end. There were, I won't say which team did not have the correct result, but I think it's more promising to use the moduli space interpretation. Finally, the two teams merge, and we are writing the paper together.
Okay, thanks.
More questions?
So I want to go back to this tree picture. So you said that the monodromy somehow acts on the trees.
Yeah.
Would it be correct to say that the number of points in generic fiber is some problem of counting trees?
Is the number of trees.
Number
Exactly.
of trees. Okay.
Is the number of decorated trees, because you have also half edges, but it does not matter. Generic fiber over real configuration of residue is just a set of decorated trees, and the monodromy acting on this fiber amounts to some combinatorial surgeries on these trees.
Okay, so what about the special fibers? Is it possible, or do you hope to be able to extract geometric information about them from some kind of pictures like trees?
Actually, these trees really correspond to the geometry of the corresponding translation structures. It is the description in terms of saddle connections. You have a meromorphic differential. The meromorphic differential induces a geometric structure. The geometric structure is more or less kind of polyhedron, okay? That can be described in terms of saddle connection, okay? Geodesic joining the singularities. And when you are over real configuration of residue, all your saddle connections are parallel. And you can deduce that you have exactly p minus one of them, okay? So the graph formed by saddle connection in your sphere define a tree, okay? Because you have p poles and p minus one saddle connection separating the poles from each other. So combinatorially, it is an embedded tree in the sphere. Okay?
Okay, but what about the special fibers? Because you said
the special fibers. Okay, the special fibers over a resonance hyperplane correspond to are formed by translation surfaces that have degenerated. They are nodal curves. Okay, so in this case, the corresponding geometric object is no longer CP1 with a meromorphic differential, but rather a nodal curve with usually two irreducible components connected at the zero of the differential. Okay, so you have one differential on each side with a unique zero.
But if your purpose is counting them, you can always smoothen the thing. You don't need to.
Yeah.
Right?
Yeah. Yeah. And our goal was actually just to compute the degree of this cover, so we stay away from this resonance looking.
You're counting graphs and the number of the. That's
yeah. Actually, Dawei Chen and Miguel Prado obtain a formula to compute the number of points over arbitrarily singular points of this stratification. Okay, so we know the answer.
So maybe one quick question is, when you said that edge shrinks,
Yeah.
which you get a nodal curve, that disk kind of gets redistributed on the other ones. So
Yeah.
I can see enumerative this makes sense because the sum of these lambda j's needs to be constant, the partial sum is constant. But then that means that the pole is somewhere else, right?
Yeah.
But you don't care because you're counting. Is that the idea? Because this is totally different.
Yeah, actually, this is a kind of idea we use to get the induction formula to count the trees. Yeah.
Okay. And then another question is, you said this moduli space of meromorphic differential form, this is has orbifold structure, but it's actually an Artemis stack.
Yeah.
Okay, but it's not anything divided by a finite group actually. It's an infinite group actually. It's not. It doesn't look like.
What do you mean exactly?
Well, looks like a point. It's like BG. There's a BC star. Some algebraic space of algebraic dimension -1. It's not. Doesn't look orbital. Doesn't look like orbital. Because these line bundles, right? The automorphism of this thing is a C star.
Yeah.
So it looks like a point modulo C star, infinitely many copies of a point. So it looks like a quotient of a point by a Lie group C star continuous group. So it is Artemis stack. It's not orbital.
No, look at the simplest example of the moduli space of differential forms on CP1 with one simple zero and three simple poles. Okay, you put your three simple zeros at 0, 1, and infinity, and you can describe completely the moduli space in terms of the location of the fourth point. And you will see what
now
you
I
get.
understand what moduli space. It's not the moduli space of the bundle.
Not
the configuration of poles on the base curve that you're from.
No, exactly. So the idea is that your moduli space can be, in principle, described in terms of the location of the roots, but to deform it in a geometrically meaningful way, you deform the periods of your differential.
Yes. Then you add, then it gets finite.
That's it.
Automorph.
Exactly.
Okay. More questions. Right? You have question? Oh. Well, let's thank Guillaume again.